So welcome again here for our second EDAX workshop at the MC 2021 in Vienna. And the last half an hour or a little bit more, we learned about our APEX software and EDS. Now, our application specialist, René de Clou, will show you a little bit more about APEX, but especially about direct electron detection and the first commercial available detector based on direct electron detection for EBSD, the Clarity. So René, you can start, and welcome to our workshop.
Okay. Yep. Welcome, everybody. I would like to introduce the Clarity Direct Electron Detection EBSD detector for EDAX. I will start with an introduction in how it works, what it can do, some examples that are not so easily shown perhaps on the microscope live. And after a number of slides, I will show the detector live. I will show you some of the image quality that you can get, and I will also try to illustrate the sensitivity of the system. So first of all, why going for direct electron detection? The most important thing here is to remove the optical path. So remove a phosphor screen where we convert electrons into light, and then you have to move that light onto the camera or the sensor somehow through a lens system, for example. So all of that is taken out. There are no distortions, so everything you see in the EBSD pattern is really coming from your sample. Now, direct electron detection is not new. It's been known and used for a long time already in mostly TEM, biological analysis, weak beam analysis, so for beam sensitive materials. And a number of years ago, it has also been demonstrated in experimental setups to work for EBSD applications. But in the SEM, that always was a problem. And one of the challenges we had there was how to get that sensor close enough to the EBSD sample. So the EBSD sample, you need to tilt your sample 70 degrees, and which means that the front of the detector, you cannot have a printed circuit board nearby. It needs to be separate from the electronics. That will allow you to reach a solid angle that is large enough to get reliable indexing. And another problem that we had to consider is the temperature. These detectors can go quite warm, and when they're in vacuum, it's difficult to cool. So that's why these initial detectors, those experimental detectors, never took off. So now we have developed a direct electron detector where we use multiple chips with a single top sensor. The total detector has 512 by 512 pixel resolution. It's a square unit, and it has passive cooling. So you can insert the detector into the microscope chamber close to the SEM, close to the sample, and it can just stay there for many, many hours at a stable temperature. Now, this is what it looks like. Here on the right-hand side, you have the EBSD detector close to a sample. Sample is here indicated 70-degree tilt. And here on the left side is a little schematic on how this detector actually works. So when an electron hits the top sensor, there's a little bit of a bias voltage over there. It will pull the charge into a pixel, goes into an amplifier, and then we're going to remove some noise, and then we can count it. Now, this noise that we remove here is below 3 kV. So the total noise level in these images is extremely low, which effectively means that we can measure and detect single electron events. And with that, you can get really, really nice EBSD patterns. There is more than 11,500 intensity levels. So in expressed in bits. It's about 13.5 bit depth, and that allows you to get a very wide range of intensity variations in your pattern. So you can go very dark, very bright, and all the details in between. So that will really give you fantastic EBSD patterns that you can use for example, dynamic simulations or crystallographic analysis. The other advantage of the sensitivity of being able to collect and detect single electrons is that you can actually collect EBSD patterns that we can index, that we can map with extremely low beam dose. So here's an example of a pattern of austenite iron with a few hundred picoamps. And when you look at the entire image, the maximum number of electrons in any one pixel is only 50. Most of them are much less than that. And what's important to realize here is that only a small fraction of all the detected electrons actually show the bands in the pattern. Most of the signal that hits the detector is background from electrons that are not diffracted in the crystal in your sample. Now, when we do the image processing, the standard EBSD background correction, we can flat field the image, we can remove most of the background signal. And when you plot that in a 3D plot, you can just make out the lines. And when we can just see them, the software can easily see them. So it's not a problem to index a pattern like this and collect a map. Now, just a few sequences of patterns. If you look here, 10 kV, 380 picoamps, with 20 millisecond exposure, you can have about 50 electrons per pixel at max. And if you go a bit longer exposure, you can see how the electron dose increases and also how the detail in the patterns increases. This is what happens at 20 kV, 450 picoamp. We get a higher dose, so we have more electrons coming in. And again, you can just see the increase in detail and contrast in the patterns. If we go all the way here to the right, one more, this is after 1 second. There's more than 6,000 electrons in a single pixel, and here 2,500. But that gives you really nice, sharp diffraction patterns. Now, just talking about the signal profile, I already mentioned that most of the intensity that we get is background, and the diffracted signal that we are interested in is superimposed on top of that background. Now, in this image, this is a raw image without any corrections, and you can see here the 4 segments that make up the detector with this cross or extra line in between. So just ignore that little spike here in the middle, and this is the intensity gradient we have over the sensor. When we then look at an EBSD pattern, also without any processing, you can see how the smooth curve of this background gets a little bit distorted. There's a little bit more signal and wiggle on top of that, and that's the band configuration that we see that we're interested in. So that's why we have to do this background processing, removing this curve underneath and only get those spikes that illustrate the bands. When you do that, then the profile gets flattened and we just exaggerate the intensity of the diffracted signal so we can see all the details in the diffraction pattern. This is with 5,000 electrons on average per pixel. And this is what it looks like with 10 electrons on average per pixel. So these two extremes illustrate the entire range of operation of the Clarity detector. You can get really, really nice EBSD patterns if you want to compare it with dynamic simulations, if you want to use it for phase identification or other crystallographic work, or if you have a material that is extremely beam sensitive, you can work with very low beam dose with just a few electrons on average per pixel, and we still get indexable diffraction patterns. So this is the pattern here on the right, only 10 electrons per pixel, but it's easily indexable. And this is what you can get when you map that. This is an EBSD map, 13 picoamp of beam current. Normally, we wouldn't think about these currents when we are doing EBSD. We typically work at best at the hundreds of picoamps, but most of the time a few nanoamp to get good EBSD patterns. But you can go already very, very low and get good results. Now, the other thing, in the beginning, I mentioned that the direct detection would remove the optical path. And not just that, it also removes the phosphor screen. This is an example pattern collected on an earlier generation EBSD detector, one of our Hikari systems. It has a phosphor screen, then a lens before the signal comes to the camera itself. And this looks like a really nice diffraction pattern of a nickel test sample. Then I just remove the detector, put the clarity on, and with exactly the same position and conditions, I get this pattern. And now you can see the difference in sharpness and detail that you can get in the bands here in the diffraction pattern. So a lot of the, let's say, slight blurriness of the edges of the bands here is really caused by the whole optical pathway and the phosphor screen, which spreads out the signal further than the original as it comes out of the sample. And you can actually see that as well when you take those patterns, you look at the profiles. This is a profile, an average profile across a band here. And you see it's quite smooth. This is the edge on one side, that's the edge on the other side. When we look at the clarity, we start to see a little bit more detail. The edges are sharper. Same here for the other ones, very smooth. We get a little bit more here. This one is more pronounced. Here you can actually see a number of the higher order reflections that are extending to both sides of the 111 band and so on. So you can do that for a number of different bands just to see the difference. And if you superimpose those, you can just see the difference in detail that you can get, and also that the bands on the clarity are sharper and narrower than what they are on a CCD phosphor screen based system. If you want to see more details, we can just retract the detector a little bit and see what happens. So here we have a pattern from ferrite. There's the zone axis. This is the place where the electrons hit the phosphor screen, or sorry, the detector perpendicularly, not the screen. And so when I retract the detector, we're going to zoom in to that part. You can see that there are no empty spaces in between the bands. It's when you look at the normal pattern, you typically see some bands and it looks like just background gray next to it. Here you can see it's only a superposition of lots and lots of bands. You can also compare that with a dynamic simulation. And in this example, the simulation actually looks a little bit more blurry than the experimental pattern. Now, that in this case is caused by the fact that we are using more electrons, a larger range of energies in the simulation, which cause the band's width to vary a little bit with electron energy. And that just shows that the actual electrons that make up the experimental patterns have a very narrow energy range, which causes these very sharp diffraction patterns. Also, looking at more details, a lot of the details can be correlated between the two pictures. Here's another one. This is platinum. In this case, I have a grain where I can zoom into this zone axis in the middle. It's the 111 zone axis, so it's a threefold symmetry. And when we zoom in there, you start to see a lot of details in the bands, and also look at these 3 bands here. This one here has a nice half moon shape, bright area. Same here, and in between you have this little arrow. So that's really what shows the 3-fold symmetry of this crystal orientation. Now, because of the sharpness of these bands and these diffraction patterns, you can also get a very nice orientation precision. So here I have a map on a micro indent, and you can see in yellow the low angle boundaries, in red slightly higher angle, and here the cam map. And if you put the scale bar on there, all these yellow lines are low angle boundaries between 0.05 and 0.15 degree. So it's very, very small rotations can be accurately determined in a normal mapping. And the red ones, the higher misorientation is only up to 1 degree. Now, then it would be nice to show you a live map example of beam sensitive materials, but it takes a bit of time to set that up, and they are so sensitive that I cannot guarantee that it's going to work. So instead, I would like to just show you a quick example of some work that has been done in the past. In this case, here I've got a few references. The example I'm going to show is the second one, the methylammonium lead iodide. That's work from Loretta from AMOLF in Amsterdam. And this is one of the samples that she worked with, 100 picoamp beam current. And this is one of the better patterns that we can get. Well, in this case, that's easy to index. And then we can beautifully index one of these flower-like structures. We see those green lines. Those are like twin lamellae in there. And it's a very, very strongly textured material. If you try to analyze this with a higher beam current, you just drill a hole in the material. If you look at a different direction, the pinkish one here on the right, that's the crystal direction sticking out of the sample, looking at you. And the other two are, this is the vertical axis, and this is the horizontal axis. So axis 1 is X, axis 2 here is Y. And you can see also here it's beautifully symmetric, where the different orientations can be reliably differentiated. Now, this one was a little bit more challenging. This is the original pattern. You just get almost nothing in there. But because we have so many gray levels to play with, we can stretch the image. And now we can start to see something. And when we then apply background correction, some additional image processing to really pull out all the details that we have, we can see the bands quite clearly. And we can index that, of course, as well. So this is the initial mapping result. And in here, these are image quality maps. We have just a few grains that produce something. Most of the area is just noise. But longer exposure or a higher beam current were just not an option, because that would certainly damage the material. So what we did here is apply our NPAR tool, which you can see like a moving average, where for every pixel in the map, we take the patterns of the 6 pixels around it on the hexagonal scanning grid, and we average those. That dramatically improves the signal to noise ratio, and then it gives us EBSD patterns where we didn't see nothing before. So just to illustrate the effect of the NPAR, here are 2 of the original patterns. These are the better ones. After NPAR, we can see a lot more detail that are easily indexable. And this is the image quality map afterwards. Remember, initially, we just saw a few of the really white grains here, and we didn't see anything else in the microstructure. And now we can easily see all the grains of these flower-like features. That's the original mapping that we had. And when we then index it, we don't get 100% indexing, but we get enough information to get a good indication for the orientation distribution in the material to help identify the performance and correlate the performance of the photovoltaic material with the microstructure. So just to summarize that, Clarity is the first commercial direct detector for EBSD, specifically designed for EBSD. It provides really good sensitivity where we can work in picoamp beam currents, gets fantastic pattern quality, and it gives you a really nice performance for EBSD pattern collection and also for mapping under challenging conditions. It really allows you to open new pathways for EBSD. Some examples I've shown, beam sensitive materials you can do. Another thing we recently did is really improved lateral resolution on bulk materials. Where doing transmission, EBSD was not an option, and we really had to minimize the interaction volume. We could work there with 8 kV, few tenths of picoamps, and really identify sub 100 nanometer microstructures very nicely. And you can work with simulated EBSD patterns, for example, for dictionary indexing, and also compare it with reference patterns for HR EBSD or strain analysis. So before I go to the live system, are there any questions? No questions so far? Okay. Then I'll just switch to my live system. And here we are. So in a previous session, Nalan showed the Apex software in the EDS mode. We had point analysis, line scan, mapping. And here on the top right, I just switched over to the EBSD section of Apex, where we have all the EBSD controls, camera control, pattern scanning, and a few more specific controls for phase setup, band detection, and system calibration. When I go to camera, I can take control of the beam. I can move my beam around, and we can see the live patterns everywhere. So this image here at the bottom shows the signal that is directly coming from the detector without any image processing. And this is the background image that we use to remove this intensity gradient. The result is here shown in the middle, the large area, that is the background processed diffraction pattern. Here on the right-hand side, we have the camera controls. Right now, I'm working at 1:1 binning, so full pixel resolution of the sensor. And I can just here with exposure time, you can see what happens. This is the live image. So if I want to see if something is oversaturated, that's the picture to look at, not the big one, because that is after image processing. So if I just make this a little bit darker. Right now, I'm working at about 1 nanoamp of beam current. So I need a little bit of time. I have here 200 millisecond exposure. So it's close to 5 frames per second. And now I can grab a new background. So I just take control of the beam. And I just do a background like with any EBSD detector that we do. So average over a large number of grains. And when I then take control again, you have really nice diffraction pattern. So this is over a twin boundary. And this is a pattern of a carbide grain. If I now go to the pattern tab, we can also look at the indexing results. And here I'm not interested in mapping at this moment. I just want a nice quality diffraction pattern. So I've increased the snapshot average for 15. So I'm averaging 15 pictures to really maximize the detail in the pattern. And here you can see all the detail in these. This is a chromium carbide M23C6 that we can index. So there's the C-axis of that crystal, where you can see a fourfold symmetry. If I now move my mouse, you can see the live image on the top right. So let me go to the matrix. In this case, this is a nickel aluminium chromium alloy with chromium carbides. And here we have a pattern from the nickel aluminium matrix. Again, very sharp. Here you can see like a little diamond shape details in this zone axis. And these are the interference lines of the higher order reflections that we can follow down this line here, for example. There's 1, 2, 3, and on this side also a few. And these are intersecting with this band that's coming this way and the one that's going horizontal. This is with a relatively high current of 1.5 nanoamp, 1 to 1.5, something like that. If I want to reduce that, I'm going to, let's say 100 picoamp. So yeah, just a moment to set up my SEM image again. So we are sure that we have a nice picture. So all the detail in my SEM image, this is the SE detector, is gone. We can still see the carbides. Right now I'm at around 100 picoamp of beam current. And if I switch back to camera, you can see the live image is not much. So let me get a new background that belongs to this signal level. And there are the patterns. Now, these are the patterns at 1 by 1 binning. So we are taking all the pixels individually. If we want to do a mapping, we can also apply a binning. In this case, let's say 5 by 5. I have a button here, cumulative binning, which means we're just summing up all the signal in the pixels. So again, let's look at that image. I can make it a little bit darker. Just get a new background for this so that it matches this picture. And we have really nice diffraction patterns at 100 picoamp of beam current. If you want to push it a little bit further, I'm now going to about 35 picoamp. Actually, you can see it doesn't change too much in the live image. It gets a little bit darker here. So let me grab a new background for that. Again, this is just live EBSD mapping at about 30 picoamp of beam current. So if you would have a beam sensitive sample, most of the time it will be able to withstand this for a certain amount of time. If I now go here, so there's the original 1 by 1 binning at 3 nanoamp, or no, was it? No, 1.5, sorry. And this is 5 by 5 at 30 picoamp. but still very indexable and not a problem to work with. Now, finally, what I can do here, I can drop the high tension. I was at 20 kV before. Now I'm going down to 8. So let me just again check my microscope image. Grab a new image. And you can already see the patterns here on the right. So my beam conditions right now are 30 picoamp and 8 kV. And I'm getting patterns already here visible. So if I now go to mode here, of course, they are not as pretty anymore as when you use a higher accelerating voltage, but you can really see the bands clearly enough for good indexing. And because of the lower kV, the bandwidth has increased. So we can push that a little bit more. So I go a little bit faster. And when I now go for mapping, I'll just let me zoom in a little bit. Just the EDS signal you see here at the bottom is also an indication for the beam current. We get 80 counts, so very, very little in there. So we really have very few electrons to work with. I'm going to set this to 0.5. We can always stop it. And I'm going to save all the patterns so we can use them later on. Oh, cancel that. I didn't want to use the chemistry actually. So you see that we do get some misindexing, but most of the grain, there's this pinkish or purple and this light blue is correctly indexed, and the patterns are easily recognizable. Again, this is 8 kV, 30 picoamp. So that's something you can work with. So while this is running, I would like to show you some maps I collected earlier, and just to illustrate the effect of using a lower beam current. And in this case, this is at 20 kV. So, and this was about 1.5 nanoamp. So comparable to my first example. And this is an image quality map, and you can see it looks very sharp. You see a lot of detail in here. And if I look at the IPF map, there's the indexing result. We have a few noise parts, and those are the areas where we just had a hole in the sample effectively. So that's where it's completely black. There was nothing there. And with the Clarity, we also support Prius imaging. So Prius means that, maybe I can just illustrate that here. So if I take a pattern, we can collect 3 images during EBSD mapping. That's one of the Prius imaging modes, where we collect the intensity at the top of the detector a block in the middle of the detector and a strip at the bottom. At the top of the detector, the image is sensitive to the backscatter contrast, so atomic number contrast. In the middle, it's very sensitive to orientation contrast and not so much for topography. And at the bottom, it's almost the electrons that travel almost parallel to the sample surface. So that is very sensitive to topography. Sorry. So if we look at those images, this is the Prius top image. And you can see a little bit of orientation contrast. We see the darker carbides and we have some brighter parts. Partly this is topography, but there are also some small zirconium yttrium oxide particles in here. If I go to the center, that shows a very strong orientation contrast and not so strong topography. And if I go to the bottom, I get stronger topography. We have the edges of those small particles here. We can see those holes a little bit better. And of course, we also have the orientation contrast. And this image is also very revealing for any remaining surface damage. So here we have all these little scratches that were left over that were almost invisible in the image quality or the Prius center image. You don't really see those here a little bit, but in the Prius bottom image, those are very clear. And if I then combine this with the orientations, or let me just copy that and put the phase map on here. So here we have chromium carbide and add the nickel. Let's put these in yellow. So we have a pretty good separation of the phases. There's a few stray pixels that didn't want to play, but in general, that works very nicely. Now, the other thing, we are now collecting a map at, what was it, 8 kV, 30 picoamp. Previously, I have collected another map at 7 kV and 200 picoamp. So it's a little bit more than that. So the original one, this is really where my surface topography and my surface damage caused some trouble. This is the original indexing on a small area. We can identify the grains quite nicely, but also quite a lot of noise in this image. And when we look at the patterns, they are quite weak. When I move my mouse, you can make out the bands. But when I just have my mouse still, it's sometimes difficult to identify the grains. So what I can do here, I can apply NPAR. So just to illustrate what that looks like. When this is the original image. So this is as measured, and NPAR changes that into this. So now we have a lot more detail. We see more bands, and that is something that can easily be indexed. We can do a little bit more. We can add a dynamic background correction. We can stretch the contrast brightness. If we want to, we can apply a whole range of additional image processing algorithms, but let's just take it simple. And when I want to just re-index this data set this way, now you can see that in most places we get beautiful indexing. There's very little noise left. There are a few places along grain boundaries where the pattern quality was just too poor, but in most places we can get really good EBSD mapping results. And this was at 7 kV and 200 picoamp. So if I compare those maps, and here you can see when I mentioned that NPAR was doing a local averaging, it takes 1 pixel and the 6 pixels in the hexagon around it. It will blur the grain boundaries a little bit, depending a little bit on the step size. But in general, you will get data that is very usable and gives you a good indication of the microstructure. And this is something that we can also apply later on to this data set. Let's just let it go for a little while longer. I'm not going to wait another 8 minutes, but just a little bit further. We can already see the grain structure quite nicely. We can see the carbides nicely, but also the diffraction patterns are really quite weak. And in this case, we know that we are capturing virtually all electrons that hit the detector. So we're really seeing that. And that means that the beam current is now so low that we only have a few electrons that actually form the bands that we can see here on top of our background image for the background intensity. So in order to improve that, we would really have to increase the beam current, or as we can do in a moment, we can apply NPAR to improve that as well. In some cases, just re-indexing and stretching the contrast a little bit more is already sufficient, and you don't have to do the averaging, but in this case we can. So I'm just going to stop this scan. Software tells me that only 10% is reliably indexed. Well, that seems to be a little bit low. You can see the color coding here. It's much more than 10%. That gives a sensible orientation solution. And when I now load the data set, that's this one. So let me close everything else and take a look what we have. So here, when I look at the patterns, they're actually not too bad inside the grain. The carbides, there's almost nothing. And this one is also a little bit more difficult because there's one zone axis right in the middle of my pattern. So it's very easy for the software to just get some rotation in there that you can not separate. So when we tried that with NPAR, you can see the difference. So there, let me remove that. And if I go to one of the carbides, the original image here on the lower right hardly shows anything, but that picture there shows it beautifully. So what I can do now, and just tell the system, okay, re-index all of that. There is still some misindexing orientation in this one grain that you could take a look at later. But the results here are quite clear. Even in the image quality, it looked originally as if this was one larger carbide grain, and now you can clearly see there's 4 of them. So already there, you have a lot of information under these beam conditions. Okay. I think that's about what I wanted to show today. Are there any questions, any comments?
René, there was already a question where someone asked, what is the probe current required for EBSD experiments, especially if you measure metal alloys?
That really depends on the detector and the pattern quality. When you are working with very clean, nice crystalline material that is perfectly polished, with the Clarity, we can work with less than 10 picoamp. On a normal detector, we typically work between 1 and 10 nanoamp of beam current. If you have a heavily deformed material, yeah, then it also depends on the microscope, how narrow the beam can be. But on most field emission microscopes, you would work somewhere between 5 and 10 nanoamp. And on the Clarity, I would work below 1. Because as we saw before, when I'm at 2.5, 3 nanoamp of beam current, then the detector easily oversaturates. So that's already too much for what I need.
Okay, thank you. Any other questions? I don't think so, René. And thanks for a nice presentation and live demo. And to all, enjoy the rest of the MC Vienna and have a good day. Thank you all. Bye.